Imagine a magician performing a trick where a coin exists in two places at once. You see the coin spinning in the air, and while it spins, it's neither here nor there, it's in a state of superposition. But the moment you try to grab it, it suddenly appears in one definite location. What happened? Where did the two places at once magic go? This, in essence, is the enigmatic phenomenon of quantum decoherence, one of the most fascinating and yet perplexing concepts in quantum mechanics. Decoherence explains why quantum superpositions, which allow particles to be in multiple states simultaneously, seem to disappear when observed. It is the bridge between the bizarre quantum world and the classical reality we experience daily. To understand decoherence, we must first grasp the fundamental principles of quantum mechanics: superposition, entanglement, and wavefunction collapse. Let's unravel these mysteries step by step. In the quantum realm, particles, such as electrons, photons, or even entire molecules, don't have well-defined positions or velocities until they are measured. Instead, they exist in a superposition of all possible states simultaneously. This is described mathematically by a wave function, psi, which encapsulates all possible realities for a particle. A classic thought experiment that illustrates this is Schrödinger's cat. The cat is placed in a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the counter triggers the hammer to smash the vial, releasing the poison and killing the cat. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, until you open the box and check, the cat is in a superposition of both alive and dead states. This paradox arises because quantum particles can be in multiple states at once, until something happens that forces them to choose. Quantum entanglement is another weird feature of quantum mechanics. When two particles become entangled, their states are instantaneously connected, no matter how far apart they are. Measuring the state of one particle immediately determines the state of the other. This phenomenon, which Einstein famously called spooky action at a distance, plays a significant role in quantum decoherence, as it ties quantum systems to their surroundings. Here lies one of the great puzzles in physics. Why does measuring a quantum system seem to force it into a single state? Physicists once thought that the act of conscious observation was responsible. However, modern quantum mechanics suggests something subtler. Interactions with the environment cause superposition to break down. This is where decoherence comes in. Decoherence describes the process by which a quantum system loses its quantum behavior and starts acting classical. It occurs when a quantum system interacts with its environment in an uncontrollable way, transferring information about its state to the surroundings. Every quantum system exists in a complex, delicate wave function that contains all possible states. However, real-world objects aren't isolated. They interact with air molecules, light, temperature fluctuations, and other particles. When a quantum system interacts with the environment, it becomes entangled with it. The environment measures the system in a sense, but without a conscious observer. This interaction causes the system's wave function to rapidly spread out and become mixed with the environment. The delicate interference between quantum states is destroyed, and what's left is a classical state. In other words, decoherence explains why we don't see macroscopic objects in superposition, even though quantum mechanics says they should be. One of the most famous quantum experiments, the double-slit experiment, is a perfect example of decoherence in action. When single electrons or photons are fired at a barrier with two slits, and no one observes them, they interfere with themselves like waves, creating an interference pattern on a screen. However, if a measuring device is placed at the slits to observe which path the particle takes, the interference disappears. The electrons behave like particles instead of waves. Why does this happen? The measuring device introduces decoherence by forcing the electrons to interact with their environment, causing them to lose their quantum superposition. One of the most intriguing implications of decoherence is its connection to the many worlds interpretation, MWI. In this theory, the wave function never truly collapses. Instead, all possible outcomes occur, but in separate, parallel universes. For example, if you measure a quantum particle in superposition, in one universe, you measure it as spin up. In another universe, you measure it as spin down. Decoherence explains why we only ever see one outcome. It prevents us from perceiving other branches of reality. However, these alternate realities might still exist, inaccessible to us. But why do we care? 1. Explaining the classical world. Decoherence solves the mystery of why quantum effects don't appear in our everyday lives. Objects like chairs, planets, and people are constantly interacting with their environment, making their quantum superpositions decay almost instantly. 2. Quantum computing. Quantum computers rely on coherent superpositions of quantum bits, qubits. However, decoherence is a major problem because it causes information loss. Scientists are working on ways to counteract decoherence using error correction and isolation techniques. 3. The future of quantum technology. Understanding decoherence could lead to breakthroughs in quantum teleportation, ultra-secure encryption, quantum cryptography, and quantum-enhanced sensors. Quantum decoherence is like a silent thief. It steals away the magic of superposition before we can witness it directly. It doesn't destroy superposition, rather, it hides it by entangling it with an enormous web of environmental interactions. While decoherence explains why we see only one reality, it leaves open deep philosophical questions. Is wave function collapse real, or just an illusion? Do parallel worlds exist, hidden behind the curtain of decoherence? Could we ever control decoherence enough to unlock the full power of quantum mechanics? As physicists continue to unravel these mysteries, one thing is certain: the universe is far stranger and more fascinating than we ever imagined.